to be part of this seminar, very successful series, and I myself have benefited a lot from watching several of the presentations, so it's good to be part of it. So today I'm going to talk about an ongoing effort in our group, what we call building the earthquake virtual machine, and specifically focusing on modeling sequences of earthquakes and aseismic slip in complex fault zones. Before I start, I would like to acknowledge the people who actually did this work. Dr. Mohammed Abdul-Majid, who recently graduated and is currently a postdoc at Caltech, and Dr. To-be Med-Shaman Maya, who will be defending soon, and also acknowledge my funding sources. So just to start very briefly, I come from more of a mechanics background, and so there's always a question of why using mechanics to understand earthquakes, don't we have enough data and observations to do this? And there are two reasons from my perspective. One is that earthquake provides a unique opportunity to study dynamic fracture at scale. In fact, as engineers like myself, we would always like to design against fracture, but when it comes to earthquakes, it's all about the fracture process itself and how it evolves. So this is a unique opportunity, but also from a societal perspective, and despite the explosion in data recently, we still operate in a data limited regime, and there's a need to fill in this gap. This is a map of large earthquakes that happened in the last 120 years, and we can only count perhaps 5 magnitude 9 earthquake, 50 magnitude 8, few hundred magnitude 7, and so on. So it's actually very limited data to make out reliable statistics. So simulations are needed to fill in this gap. And like anything in simulations, from a modeling perspective, we'd like to start with an idealized systems. But the reality is fault zones are really complex entities. Whether you think of a fault zone with a single slip surfaces or multiple slip surfaces, we see that there are some persistent localized zones, but these zones exist in dynamically evolving structure, and there's distributed and discrete damage, and the whole system is operating far from equilibrium and is continuously evolving. There's some long-lived statistical properties, but to reach these statistical properties, there is an evolutionary trajectory that varies from one fault to another. And if we accept this picture, then we also accept that the volumetric and deviatoric deformations are naturally coupled. So this idea of just pure slip on a planar surface may not longer hold. And also that the processes, of course, are depth dependent because rock strength is pressure sensitive. And it turns out, of course, that this complexity is important for some fundamental questions. I will show you here a thought experiment. What you are going to see is a fracture that is initiated in a complex fracture fault network. And I would like you to see how it's going. What you are going to observe is the particle velocity. So we start the fracture somewhere at the middle, and it will start propagating bilaterally, but then it will get frustrated by a network of faults. And you could see now that the fracture path becomes very complicated. You start getting triggering in remote places, interaction between rupture fronts and waves. And so you get a very complex wave pattern, in addition to fundamental questions related to path selection, radiated energies, and stuff like this. And it turns out, recently we have been looking at the Turkey earthquake, and so this complexity is not only a theoretical exercise, it has important implications for hazard. If we look at the southern part of the East Anatolian fault, it's very complex geometrically, and this is the part that experienced intense shaking. And if I play this movie again, you would see that the rupture front is coming as a sub-Rayleigh, but then as it approaches this geometrically complex region, it starts dynamically triggering branches. You could get some sort of super shear transition accelerated because of this kind of geometric complexity and so on. So this is also have some practical implication. So how to incorporate this complexity? This is where this vision for the virtual earthquake machine comes into play. Unfortunately, or fortunately, looking at a single earthquake rupture simulations and modeling has been very useful, but it cannot capture everything because it depends, the results in single rupture simulation depend on initial conditions. And we may think of randomizing the initial condition to explore different scenarios, and that works and helps a bit, but it assumes that the system is ergodic. So by exploring enough initial conditions, you could explore the different final states, but there is no guarantee that earthquake faults are ergodic actually. So what we think is the right framework to simulate this is what we call sequence simulations, where we start with some arbitrary initial condition and let the system evolve to explore the proper space in which the system needs to be sitting in order to be able to generate these long-lived statistics that we observe in nature. And so the ingredients of this virtual earthquake machine, we should have faults and fault zone because that sets the geometry aspect. We should have constitutive description for the bulk because like whether elastic, plastic, damage mechanics, because that's what governs how the bulk responds to stresses and generate deformations. And then we solve these systems of stresses and deformation by looking at the governing equations here, the governing equations for the balance of linear momentum. And a key ingredient in this cycle is the word evolution here. We would like actually to carry out this simulation in order to understand the co-evolution of faults, bulk, and seismicity in a consistent way. And actually, people have such vision on their mind for a long time. And I'm just here listing some selected work related to the idea of modeling sequences of earthquakes and aseismic slip. It's not comprehensive by any means, but our vision is to do this with high resolution because we understand that the nonlinear physics near the faults is actually what governs the fault mechanics. So we need to resolve fault zones with high resolution. We need to incorporate inertia effects because these are important for the seismic phase. We need to engage the bulk through its nonlinear response, so going beyond elasticity and even beyond, eventually beyond continuum plasticity. The fault zones are geometrically complex, so perhaps we would like to also incorporate multiple faults. And eventually, we would like to have the opportunity or the option that our fault zone itself can evolve geometrically by generating branches, roughnesses, and so on. So evolving fault network. So this is the long-term vision, and I will try today to give you some overview of parts of this vision and how we are moving towards realizing it. But of course, this is very nice to think about, but there's no free lunch, right? It's not an easy process. And one of the major challenges that we encounter as modelers is that there's a wide range of spatial and temporal scales involved in the earthquake problem. There is temporally, we can think between milliseconds to years. That's the scale of the seismic cycle. Spatially, we need to resolve areas near the rupture tip where there is extreme gradients of stresses and deformation, which we call the process zone scale, which usually could be even sub-millimeter scale up to kilometer scale of the faults. And then the rates also ranges from nanometers per second to seismic rates, which is meters per second. So there is orders of magnitude of spatial, temporal, and rate scales here. So it turns out that, of course, this is a hard problem, which may not be solved at once, but there are some important problems where we can invoke some sort of separation of scale because complexity seems to be relatively localized. And by relatively localized, what I mean here is that, for example, if we look at fault zones, the fault zone width could be tens to hundreds of meters, whereas the fault length could be many kilometers. So the area where complex material properties, complex geometry, etc., exists seems to be much smaller than the overall dimensions of the system we are interested in, where waves propagate and strain energy changes, but also seems to be a bit wider than what you can represent by lumping on the fault surface as an effective friction or cohesive load. So it's kind of in between these two extreme scales. And so to exploit this sweet spot that we are interested in, we developed a special numerical scheme. And so traditionally, when we think about modeling earthquakes with nonlinear geometry and nonlinear rheology, we would do finite element simulations. We choose a large enough domain for the simulation and impose absorbing boundary conditions here. And we discretize the domain, say, by finite element or finite difference. But what we opted to do, because of our focus on this class of problems where complexity is relatively localized, is we said, well, let's just focus on the fault zone. Let's actually kind of cut this area here around the fault that includes the complexity. And we call this our virtual strip. So we cut it. This area is relatively narrow. We can discretize it with whatever domain-based discretization we are interested in, finite difference, finite element, discontinuous Galerkin, whatever. But the idea is the exterior half spaces now are not explicitly modeled. Of course, you cannot throw them away because the exterior half spaces is where the interaction and long-range interaction through the waves and stresses exist. What you can do instead is to represent the effect of the exterior half spaces, the upper and lower half space, as a boundary integral equation. So on the boundaries of the virtual strip, you could impose integral equations related to, that relates the stresses to deformation, and that would represent the boundary conditions for your virtual strip. Now, this is an exact boundary condition because these integral equations are exact representation of the elastic interactions in the exterior half spaces. And all what's left then is to try to impose continuity of displacement and traction on this boundary. And through exchange of the displacement and traction, we can actually just focus on the resolution within the virtual strip, and the effects of the exterior half space would be encapsulated through the boundary integral equation. So that is what we opted to do in the spatial decomposition, and leveraging some background experience we have with the spectral formulation of the boundary integral equation. And I know Nadia Lapusta was giving the seminar a couple of weeks ago. By choosing our virtual boundaries to be straight, we can actually solve the integral equation in the Fourier space. So that makes them very fast and also accurate. Temporally, we use an alternating quasi-dynamic, fully dynamic integration scheme. What this means is that when accelerations matter and seismic velocity and the velocities reach a seismic threshold, we solve the equations of motion explicitly. We solve the dynamic equations of motion with the accelerations, and we use explicit time integration. Once the velocities drop and accelerations becomes no longer important, we use a quasi-dynamic approximation to resolve the aseismic deformation. And then we alternate between these two schemes through a switch threshold. Like we put a threshold, say, for the maximum slip rate on the fault that allows us to go from one simulation domain method to another. And the method has been extensively verified using SCEC benchmark problems. And for those who are interested to know more about the details of the method, I invite you to look at some of these papers that I included here. So let me give you a few examples about how we use this method to understand this interplay between the faults and the bulk, especially the nonlinear behavior of the bulk. So my first example is related to coevolution of fault slip and bulk plasticity. And the example I will show here is starting from a simple planar fault that has patches of velocity weakening and velocity strengthening rate and state friction, coupled with an elastic viscoplastic bulk in mode 2 approximation. So the bulk is also subjected to some state of initial stresses that can be characterized by the maximum principal stress and the orientation of the principal stress. And we would like to understand, if we start running this sequence of simulations of earthquakes and aseismic slip while having plasticity in the bulk, what would be the effect? And just very briefly, the plasticity we are using is Drucker-Prager plasticity with a viscoplastic relaxation. And we know from a series of work in the 2000s and 2010, what we expect when we run a dynamic rupture with off-fault plasticity. Due to the pressure sensitivity of the Drucker-Prager plasticity and the fact that the yield strength depends on the mean stress, this introduces an asymmetry in the potential distribution of the inelastic strain. So if I look at a right lateral fault like this, there's a compressional quadrant in this region where the normal stress or the mean stress is becoming more compressive. There's a dilatational quadrant where the mean stress is reduced due to the tensile perturbations. And because of the dependence of the Drucker-Prager strength criteria on the mean stress, we expect that the plasticity would be accumulating more in the dilatational quadrant. That, of course, depends on the orientation of the maximum principal stress, as Templeton and Guy showed. But in general, we expect that on the tensile quadrant or the dilatational quadrant, it's more prone to generating plastic strain. Now, that's what we expect from single dynamic rupture simulation. But let me show you what we see in some cases when we run sequences of earthquakes and aseismic slip with plasticity turning on. So on the top panel here, you would see the slip rate on the fault. On the middle panel, you would see the plastic strain accumulation in the bulk. And in the bottom panel, you would see the mean stress as it's evolving with the sequence. Okay, so I will click on the radio on the button here. Of course, as in sequence simulation, you would start seeing a wide range of slip rates from nanometers per second to meters per second. But interestingly enough, you start seeing as a result of multiple earthquakes that the plasticity doesn't have plastic strain distribution, doesn't show this asymmetry that we expect from a single dynamic rupture. In fact, due to the accumulation of multiple events and having events of different sizes, events propagating in different orientations, you'd start seeing that more or less you get damage on both sides of the fault here. You could also see some evidence for localization and band formation and so on, but more or less you get a kind of asymmetric pattern here for the plastic strain distribution. And that is coupled with actually very interesting feature that we may like to talk about later related to the evolution of the mean stress in the bulk. There's also the mean stress. We start with some initial values consistent with the applied tectonic stresses, but then this evolves due to the feedback between plasticity and the mean stress. So what do we expect when we look at the seismic history in these simulations? What I will show you here are contours of the slip rate. Each one of these figures represent multiple events that we generated during the cycle. On the horizontal axis, that's position along the fault. On the vertical axis, that would be the time step. And we like to put it in time step because we need many time steps to resolve the dynamic rupture. We need less time steps, or the time step is larger to resolve the aseismic phases. So in order to be able to see the seismic events that happens in seconds within years, we need to plot as a function of time step rather than the absolute time. But what we observe here is we can get a very rich behavior from almost periodic seismicity to a chaotic distribution of seismic events with broad distribution. And that depends on the relative strength of the bulk compared to the strength of the fault. And the strength of the bulk is measured by the yield strength, which is here kind of parameterized by the angle of internal friction and cohesion. So for example, by varying the cohesion, we can make the bulk stronger or weaker, and we can observe this transition from periodic events where you have more localized deformation on the fault and less plasticity in the bulk to a broad range of seismic event sizes here as the bulk becomes weaker and the deformation becomes more distributed. So the bulk is now engaged in having more plastic deformation. And one may actually inquire whether this kind of partial ruptures and events of different sizes may be emerging because plasticity dissipates a lot of energy. And in fact, what we have discovered is that in order to get fast enough ruptures, the contribution of off-fault dissipation to total energy budget has to be small, like maybe a few percent. And what I'm showing you here, for example, is for different viscosities that we introduce in order to regularize the Drucker-Prager plasticity, the plastic energy dissipation is of this order, 10 to the power 8, whereas the frictional dissipation on the fault is 10 to the power 10. So there is actually 2 orders of magnitude difference. So plasticity contributes a few percent of the total energy dissipation at least, right? And so why would earthquakes stop then with the plasticity and not in elastic simulations? And what happens is that off-fault plasticity, at least in the models we are using, caps the stress concentration at the rupture tip. So if you have an elastic system, you can actually concentrate the stress ahead of the rupture tip. There is theoretically no limit, but of course it's limited by the cohesive load that you are using. And so this concentration of stresses that grows with the rupture length allows the rupture to propagate further. And this is why in many homogeneous elastic sequence of earthquake simulations, you get this kind of periodic events that are fault spanning. Whereas in an elastic, perfectly plastic case, you get this kind of capping of stresses at the level of the yield strength. And this capping of the stresses deprives the rupture tip from having enough energy to continue propagating and kind of allows the rupture to be quenched and self-arrest if conditions are permitted. So this kind of evolving stress heterogeneities due to this interplay between the rupture tip and off-fault plasticity causes this self-arresting mechanism, even though the plastic dissipation is just a few percent of the frictional dissipation.
Ahmed,
yes.
Chris, sorry to interrupt. Just a quick point of clarification. So you're telling us about the impact of strength, and I'm curious, maybe I missed it. Are we talking about both the frictional strength and the mean stress dependence of Drucker-Prager, or
that's a great question, and it becomes very clear if we look at anti-plane problems, but even in the in-plane problem, there's the bulk strength that's parameterized by the yield function of Drucker-Prager plasticity, and that's parameterized by the cohesion and dependent on the mean stress. Whereas there is also a measure for the fault strength, which you could kind of think about it coming from this reference friction multiplied by the normal stress. So there is some sort of an ambient strength for the fault, and how far the bulk strength from the fault strength controls this cycle evolution. If the bulk is much stronger than the fault, then it remains relatively elastic, and most of the deformation will be accommodated by the fault. If the bulk becomes weaker, not necessarily weaker than the fault, but the difference between the fault strength and the bulk strength decreases, or the proximity to failure increases, then you kind of get this kind of more heterogeneous rupture distribution.
I see. Thank you. Okay, and the friction is Coulomb.
In the friction on the fault is rate and state friction, but in the bulk, this is Drucker-Prager, which is very similar to Coulomb criteria. Yes.
Gotcha. Thank you.
Ahmed,
Yes.
Sorry, this is
Sure.
Massimo. So,
Sure.
do I interpret right that your crack, the slip velocity looks like a crack model, not a pulse?
In this case, that is true. This is a crack model. We use just for now the Dietrich-Rowena formulation for rate and state friction. So pulses will not emerge spontaneously, except if we start adding some kind of low velocity fault zone or something like that. But this is so far, most of these ruptures that we see in our models are crack-like.
And yeah, thanks.
Yes.
One more question. When you say that the plastic work is a small fraction of the frictional work, are you comparing it to the frictional work on the bulk along the whole fault, or just the excess at the tips?
Oh no, that's another excellent point, and I haven't covered it, but we compare it to we compute the plastic work in the bulk as well, and the frictional work along the fault surface that is failing, because there are some frictional work coming from the velocity strengthening part that is continuously slipping. So we compare this in the bulk, both of them, but this is something we want to explore, and it might hold another key for explaining this is that we can compare the local co-seismic plastic dissipation compared to, say, the changes in energy at the rupture tip as well. And this could be kind of comparable, but we haven't studied that in detail yet.
Great, thanks.
So, but this is not the whole story, actually. So I mentioned that in order to get fast enough slip, we need the plastic dissipation to be low. But what if we did this experiment, continue reducing the bulk strength so that it becomes closer and closer to the fault frictional strength? Then we start seeing emergence of a spectrum of slip from cases where the fault becomes completely locked and all the external loading that you are putting on the system is being accommodated by plastic deformation in the bulk, to emergence of slow slip, to some sort of repeaters, to a mix of fast and slow slip, to heterogeneous rupture combinations, and eventually to periodic ruptures when the bulk strength becomes far enough from the fault strength. So this is another interesting aspect that we need to keep in mind when we are thinking about the spectrum of slip on the fault. Of course, there might be effects of fluids, there might be effects for frictional heterogeneities, but also this relative strength of the bulk compared to the fault seems to be able to regulate seismicity on the fault, from shutting it completely and accommodating all the deformation as bulk deformation, bulk inelastic deformation, to the other extreme when we have elastic material where all the deformation is localized on the fault and none is happening in the bulk, none of plasticity is happening in the bulk. And so this kind of transition, when we start analyzing energy partitioning in cases where the fault becomes locked, or when we have slow slip, the plastic dissipation becomes a considerable part of the dissipation budget. So if we have large enough plastic dissipation, then we expect to start seeing these kinds of slow slip, or even that the fault becomes completely locked. Plastic dissipation becomes smaller and smaller. We start expecting emergence of faster slip and slips that propagate through significant portion of the fault. So let me just show you a couple of movies related to this, what you will be seeing here that is also related to this effect of plasticity, you could start seeing intermittent nucleation. So this is something that may be attributed historically to heterogeneous friction, which in this case would be just a set in a kind of a static heterogeneity. But here the system is dynamically evolving. And what I would like you to observe is that in the top here, you would see the plastic dissipation, the plastic strain. In the bottom, you would see the slip rates. And let me start from here. So here is a rupture that is start to nucleate and propagating bilaterally, but you would see that it's pinned on its left end because of this kind of plastic strain accumulation. And then as time passes, you would see some sort of jumping ahead of the plastic strain blob that was formed. So the plastic strain zone kind of pins the crack. The crack wants to propagate, it accumulates stress concentration, and this stress concentration allows the jumping of the rupture front and renucleation ahead of the plastic strain. And you start seeing these kinds of blobs of plastic strain temporarily pinning the rupture tip and causing this jumping until the rupture accumulates enough energy and stress concentration to just zip through the rest of the fold. So let me just do it again here quickly. So you see this little crack nucleating, you get temporary arrest, you get jumping, and eventually, and this process, by the way, it lasts for hours. So this kind of failed nucleation, intermittent nucleation, the desire to kind of get the rupture starting, but not being capable of, is a repetitive process. And eventually the rupture can break through and formulate and propagate through the rest of the fault. We also kind of observe something a bit surprising here. We expect plasticity to make things smoother. Remember, we started with a planar fault, but what we observe here is because of this kind of asymmetry in the co-seismic plastic strain distribution, and because of the heterogeneity of the rupture length distribution, we actually start seeing some sort of a self-roughening mechanism for the fault surface. So here I'm plotting how the fault looks like at the end of the simulation. Initially, the fault is just perfectly planar, but by the end of the simulation, we start seeing this kind of corrugation in the fault surface due to this interplay between the rupture propagation, the plastic strain that's asymmetric during the co-seismic propagation, and that leads to some sort of local rotations in the fault strike, and also the fact that the fault ruptures now can arrest within the fault length, and whenever the rupture is arrested, it actually produces some sort of local rotation in the fault strike. And associated with this evolution of the roughness of the fault surface, we also observe that the normal stress on the fault becomes very heterogeneous too. So there's this interplay between an evolving stress heterogeneity on the fault surface with the plastic strain accumulation in the bulk, and this feeds into the non-planar evolution of a non-planar geometry of the fault surface. We could also
Ahmed,
yes,
sorry,
yes.
But your, if I understood well, your constitutive relation, your rate state friction that you assume on the main fault does not account for normal stress changes.
Does not account for, no, it can account for normal stress changes, because the rate and state friction, the strength in the rate and state friction is the normal stress multiplied by the friction coefficient. And the friction coefficient is the one that depends on the slip rate and the state variable. We still have the prefactor in the normal stress too.
Yeah, but your evolution equation does not include normal stress change.
On the state variable, yes. We don't assume that the state variable depends on the normal stress. That's true.
Okay, so it's on. Okay, exactly. This was my question.
No, and I would love to talk to you about that, because we did work on some other formulations for friction from shear transformation zone for gouge. And in that case, the state variable actually emerges to be dependent on the work rate. And so it incorporates the normal stress. So I would love to talk with you and Alan about this. So let me. And so just continuing here, we could also do standard kind of qualitative comparison with observations. For example, the decay of inelastic strain as a proxy of off-fault damage seems to be qualitatively agreeing with what people, when they go and measure the fracture density decay as a function of this density, as a function of distance from the fault, seems to have this kind of exponential, or in this case, a power law decay. And this is similar to what's observed in fault zones as well. We also observe that the width of the damage kind of saturates with the slip. So initially it grows with the slip and then potentially saturates. And that's also kind of in line with some field observations. So let me just perhaps I take 10 more minutes to give you a few other examples where we are expanding this framework for simulation, because we are excited about the possibility of being able to look at this evolution and also make new predictions like the self-roughening or mechanisms for transition between slow and fast slip and so on. But also we would like to move beyond a single fault and start, as we mentioned, explore fault zone geometric complexity. So the next thing that we started exploring is to study fault step overs. So a fault step over geometry is that you have two parallel faults that are separated by a gap and they have some overlap in between. This fault zone could be a compressive step over, like for example, for these kind of right lateral slip, the area sandwiched between the two faults is under increased compression, or it could be a tensile step over, where for this kind of right lateral, again, fault slip, this area sandwiched between the faults are actually subjected to some sort of tensile perturbation. So that's a tensile step over. And I will just give you a few examples of the results. There is a paper under review. And also I would like to mention that Pierre, Harsha, and Raoul studied some version of this problem before in the quasi-dynamic limit and for elastic bulk. So here we are extending that to the fully dynamic framework, as well as looking at off-fault plasticity. And you would see here, for example, this is on the top, you get the compressive step over, the bottom, you get tensile step over, and you could track the evolution of the fault zone as a function of time. As the slip accumulates and earthquakes happen, you could see, for example, in the compressive step over, that the two faults kind of grow away from each other, like repulsive cracks here. And as the slip keeps accumulating, you start accumulating more plasticity in the overlapping region. Could also see some sort of a growth of the fault along its strike and so. So it's a very dynamic system here. On the other hand, in a tensile step over, what we observe is that the plasticity kind of accumulate initially towards the two faults. So instead of growing away, the faults tending to growing away, these are like attractive cracks where the plastic strain tends to join the two faults together. And as we keep slipping, more and more plasticity is accumulating. So there's significant damage that we expect to occur in this overlapping region. And with these simulations, we are capable of quantifying the probability of jumping that could happen in, say, compressive versus tensile step over. And as expected for these systems, it turns out that, of course, there's a higher probability for jumping in tensile step over. But interestingly enough, plasticity facilitates this kind of increased probability. So as you accumulate more plastic strain in the system, and because of the way this plastic strain is accumulated within the gap region, you actually facilitate more jumping compared to, say, a linear elastic system. So we need perhaps to also rethink about the conditions, and this is still preliminary work, but the conditions that facilitate fault jumping and how it depends on the properties of the bulk and how that relates to the distance between the two faults. So another thing that I can show here is when we start kind of experimenting with the geometry of this step over, we do see emergence of features like multiple faults connecting the two faults. So as we make these two faults getting away from each other, we give it an opportunity for strain localization to emerge and become clear. So the fault here, you could see emergence of plastic bands at the ends. This keeps growing as a function of time with subsequent seismic events. And we could see some sort of these kind of faults emerging in the system. These are not real faults because here we are just modeling it as plastic strain. But if we use, as I will show at the end of the presentation, if we use some sort of a damage model or phase field, these would actually be real faults connecting the two pre-existing faults together. So again, this is just a way to look at the seismogenesis of fault zone as it emerges and its interplay with the other characteristics of the system in terms of seismicity and hazard. Maybe I can skip this movie and show you a third example we have also started looking at, and it's related to, well, fault step overs are one step up in geometric complexity compared to a single fault, but actual fault zones are really far more complex. So for example, this is a schematic of a fault surface with multiple kind of cracks and secondary faults surrounding it. And we would like to understand how the system evolved as a function of time and the partitioning of deformation between the main fault and the secondary faults, sequences of foreshocks, main shocks, aftershocks, and how they emerge and so on. So what we did here is we consider, say, a single planar fault surrounded by multiple secondary faults that are randomly oriented, but randomly oriented about the orientation of the maximum shear stress. And remember, we are doing this all with our hybrid scheme, and that allows us to put a lot of resolution in this narrow region and allows us to add these multiple faults as well. So that's one advantage of being able to kind of separate the scales between the elastic half spaces and where the complexity is happening. And again, this whole system is subjected to some sort of an initial background tectonic stresses. So each of these faults receive their own normal stress and shear stress that's compatible with the background tectonic stresses. And then we just let the system evolve as we have been discussing before. And what I'm showing here in these little kind of subplots, these are again, the slip rate contours in the secondary faults, and this big one is the slip rate contour on the main fault. And you would see from these plots that, well, these secondary faults get occasionally activated or occasionally can host their own little earthquakes, as observed here, for example, in these kind of red co-seismic activations. The effect of having these secondary faults on the main fault is that we start getting partial rupture and more complex sequence of earthquakes on the main fault compared, for example, to the case of having just the planar fault without these secondary faults around it. If we have just the main fault, then we will get these kind of fault spanning periodic events. But because of this interplay between the main fault and the secondary ruptures, this introduces this rupture sequence complexity. However, let me just show you something here, perhaps first through the movies, and then I will show a couple of slides, because again, it's not that simple. And what we observe is that the long-term evolution of that system could be really different from what we observe in the initial stages. But let me just show you this video here. On the top, you would see the equivalent plastic strain. On the bottom, you would see the contours for the velocity. And here we are just focusing on the seismic slip rates so that we can see how events can cascade from secondary faults to main faults and vice versa. So let me show you too. So this is, for example, an event on a secondary fault, and it generates its own plastic strain. It kind of redistributes the stresses to the surrounding secondary faults and starts getting these cascading events. Eventually, the main fault could be triggered as well. And in the meantime, you start seeing this evolution of the plastic bands from the ends of the fault, kind of trying to connect this initial seed for fractures. So my initial distribution of fracture is not stable in some sense. It actually tries to grow and connect with one another. And if we have the capacity to model these as true fractures, we would observe that the evolution of the system is merging towards this kind of coalescence of some of these cracks. So we see here, for example, an event on the main fault. And then after a while, you can get another event. You can get events triggered on the secondary faults and so on. So this hierarchy of seismicity, or the range of seismic events, is partially motivated by this interaction between the secondary complex features and the plastic strain in the bulk as well. If I show you the whole sequence, we also observe that not only the seismic events gets migrating from one fault to another, but aseismic slip also gets to migrate from secondary faults to main faults. There is also triggering of this aseismic slip. So here, the scale for the velocity is actually not capped. So the scale of the velocity is changing. And currently, for example, it's 10 to the power minus 3, goes down to 10 to the power minus 10. So you'd start seeing these kinds of migration of aseismic slip, as well as the cascading seismic events that I showed in the previous slides. So now by pushing these simulations, we could start understanding the interplay between geometric complexities and earthquake sequences, partitioning of slip between on-fault, main fault slip versus off-fault deformation. And this off-fault deformation is also not one family. Off-fault deformation partially can be localized as slip on these secondary faults, but also could be localized as plastic deformation on the edges of these secondary faults. And you could see that the plastic strain distribution in this case is very different from the one that I showed earlier when I just had a single fault without these multiple branches. So damage patterns in fault zones could also kind of tell us about underlying geometric complexity too. So this is a schematic, for example, of how this kind of complex fault network is emerging. And what I wanted to show maybe in this slide and the next one, these are my two last slides, is that what I mentioned here, we can look at the sequence history. So here modeled over 13 years, you could see much more complexity in the beginning. These events, these small cracks host their events, they get activated, etc. But as we evolve towards later in the cycle, the system actually becomes well-behaved, more well-behaved, in the sense that the system starts generating these kinds of periodic events. So because once you exhumed the secondary faults and generate enough plasticity around these secondary faults, they may not be susceptible to triggering anymore. And then you end up having to deal with the main fault carrying most of the deformation. So there's something we are currently studying about this transition mechanism or maturation of the fault zone. Initially, the complexity plays an important role in producing complex seismic sequence. But as the system evolved, we are observing, say, for these parameters, we are observing less complexity because the bulk itself was relatively strong, and mainly our secondary faults are where the conduits for carrying of fault deformation. Once these conduits are turned off because of the plastic strain distribution around them, they start actually shedding most of the deformation on the main fault. And you could see that the main fault now, occasionally you can get partial rupture, but most of the events becomes fault spanning events, and there's less and less activation on the main fault. They can be triggered a bit, but less activation there. But this is, again, and this is the beauty of having this kind of a numerical experiment, this again depends on the characteristics of the secondary faults. So if you start having larger secondary faults, so you are starting to look at interactions of fault systems, perhaps the deactivations of these secondary faults doesn't happen that soon. And we can still, although we are still running these simulations, but we can see more complexity kind of persistent over longer period of time if the secondary faults become longer. If I added into the system longer secondary faults, then we can actually start seeing foreshocks and aftershock sequences, but we don't know yet when would that system transition to a fully mature fault, or whether it will transition to a fully mature fault. So we need to run these simulations long enough to start kind of characterizing the maturation process, because in some cases, it actually can persist in its complexity. And in other cases, as I showed in the previous slide, it just transitioned into a simpler periodic, almost periodic system. So finally, I just would like to show that we are also working on this along these lines, and I have repeatedly mentioned that what I showed previously were plastic strain distribution. So this is not actually fracture. There's no kind of localized slip in these cases or degradation of elastic properties, which we all know is happening in fault zones after big earthquakes. So in order to move towards incorporation of these additional damage mechanisms that include inelastic dissipation, but also degradation of elastic moduli, we have been collaborating on developing a phase field model for fault nucleation and growth, but which is consistent with rate and state friction. So in these phase field approaches, we measure degradation. It's a thick crack, basically, approximation, but more consistent with Griffith criteria. So instead of just modeling cracks as localized zero thickness interfaces, they have a finite thickness, but then in our new formulation, we would like to make this behavior consistent with rate and state friction. So we developed this kind of rate and state friction informed phase fields model. And in that case, we can get qualitatively similar results to the plasticity simulation with one big difference, is that in these bands that you are seeing here, these bands actually have a damage parameter. And what this means is that within these bands, you get a degradation of strength and elastic moduli, which is more consistent with what we would expect for faults and the area surrounding the fault region. So this is what we have done so far in this case, is basically just in a single rupture simulation, but we are trying to push that and integrate it into our sequence simulation to study the interaction. So let me finish here. I would like to conclude. I think it's an exciting time for earthquake science, and especially modeling, because the kind of simulations we currently can do pushes, as a community, it pushes the frontiers of what is possible through virtual experimentation compared, say, to what we were able to do 40 or even 20 years ago. And with these advances in computation modeling, we will be able to probe the co-evolution of earthquakes and fault zones. Hopefully, we can use this to determine what's important and what's less important. We can identify potential candidates for observations and measurements, and we could also kind of incentivize more data collection for validation, model calibration, and harvesting. And we are doing these kinds of high-resolution deterred simulation in the hope that we eventually can actually also construct reduced order models to encapsulate this complexity. We don't expect that we would always need to run these complicated models, but we can find a low-order approximation that can actually encapsulate the observed complexity. And hopefully, when this is successful and we are able to incorporate these kinds of complexities, the next generation seismic hazard models are going to be better constrained and hopefully more predictive. Finally, I also see some opportunities for research here that I would love to discuss with you. There's an opportunity to incorporate this kind of nonlinear material response now, not only on the scale of a single rupture, but on a scale of a sequence of events. So going beyond elasticity to incorporate plasticity and damage and in sequence simulation, and there's definitely an experimental need to characterize the properties of this nonlinear rheology. I haven't touched on fluids today, and it's a topic that I'm very interested in and dear to my heart, but fluids are important and are real, and we have experts here today that have shown us how important these are, and when incorporating fluids in this framework, which is possible, we expect to see richer behavior and more impact on the evolving complexity. And in fact, the effect of fluids on damaged mechanics is even more important than coupling fluids with elasticity. So this is a frontier that I think requires lots of work to understand this interplay between fluids and nonlinear rheology of rocks. We also need to look into these methods and criteria for fault growth, branching, and healing. I have shown some initial progress related to phase field approximations, but we definitely eventually need to move beyond this continuum plasticity approximation or continuum damage model. My simulations are deterministic in the sense that they can have some numerical perturbation errors, but we are not intentionally adding stochastic perturbations in the system. And I think it's an important topic to think about, because when I model this fault zone in isolation from the surrounding other faults, right, then we expect to have some sort of indirect interaction that's not completely resolved within my sequence simulation. I could get fluid pumping, I could get stress perturbations from distant earthquakes and so on. So eventually it will be important to think about sequence of earthquakes in the ensemble framework. So we need to run many sequences and try during the sequence to add these kind of stochastic perturbations along the way. And finally, I'm of course excited to be presenting today because in some sense, the FEAR Observatory is an experiment that we expect to shed light on a lot of near field physics that are needed to constrain and inform the models that I have, or test the predictions of the model that I have shown today. Most of the work that I presented today hinges on this effect of the near field physics on the rupture mechanics. And this is an area that we are relatively have sparse data on, but we need to get closer to faults in order to be able to collect data that's informative and constraining enough for the rheology and the dynamics that we expect to see in fault zones. So I stop here and I will be very happy to take any questions. Thank you.
Excellent talk. I'll invite people to unmute and join me in thanking me for thanking Ahmed for a fabulous talk. Really, really nice talk.
Thank you very much. Yeah.
I will invite everyone to do what I just did. Please join in with questions, especially early career people. I suppose there'll be plenty of people who will raise their hands here who are a senior and whatever, but you don't need to be. In fact, I'm going to move you up in the chain if you're someone who I know is an early career person. So anyway, Ryan Schultz, please get us started.
Yeah, so very nice talk. I just have a quick question, let's say, about one of your concluding points there. So trying to focus on what sorts of things you would need to see to get build these better models or do the reduced order physics. From your point of view, what would be the ideal thing for an observationalist to point out that would really get at the heart of finding out what's important for this plastic deformation and maybe even disentangling it from other effects like the fluid related effects?
Yes. That's an excellent point, and it's something we have been thinking about. Although we are not an observational person, but for example, there are many parameters that goes into these nonlinear bulk models that needs to be constrained. And of course, a starting point is to constrain it in laboratory experiments, but also if we have near field, say, seismic arrays and boreholes, then we probably can capture their effects on the near field ground motion. And because if you are close enough to the fault, you would start seeing the impact of these deviations from elasticity on ground motion characteristics as well as on deformations, right? So I think boreholes and dense seismic arrays in the near field are important. And once we have those, I think we could also start kind of discovering additional deformation modes that get, say, washed out in the far field. So for instance, something like volumetric deformations and dilatancy, at least the hope from nonlinear rheology, this extends perhaps to tens of meters or hundreds of meters. So we could kind of pick that up. For fluids, it's even more challenging because in fluids, these kind of diffusion length scales are really small and maybe we'll never be able to come close enough to the fault in order to measure, say, dilatancy to fluids and so on. But at least if we are within 100 meters to a kilometer away from the fault, then we could start seeing these imprints for deformation modes that are correlated with nonlinear bulk behavior. So I do think that collecting data on deformation fields in near faults could inform and constrain these models, and that should be supplemented by our traditional program of getting rocks and testing them in the lab and characterizing their strength envelope at different strain rates and fluid conditions and so on.